Hello friends, welcome to our channel HTLT Electrical and Electronics Engineering. Today here I am going to discuss about earthing system part 2. Earthing system part 2. Here I am going to discuss about system earthing or neutral earthing. Here is ungrounded neutral system. Though previously some power systems were operated with neutral point unearthed, the general practice now is to operate the power system with neutral point connected to earth, either direct or through some current limiting device to prevent the insulation failure due to high transient voltage at the time of earth fault at some other location, equipment failure and arcing grounds. In a perfectly three-phase transposed line, phase conductors have some capacitance to ground CR, CY, CB. Here is a phase conductor, here is a ground, there is three capacitance CR, CY, CB. And phase to neutral voltage VR, VI, VB. Here is the VR, VI, VB and the capacity currents IR1, IY1, IB1 will be equal in magnitude and displaced at 120 degree. If the load is balanced and the conductors are symmetrically spaced, then under normal condition potential of the transformer neutral will be equal to that of earth. This is the transformer neutral. Its potential will be equal to that of earth. And here is the IR1, IY1, IB1, IR1, IY1, IB1. This capacitive current flows to the earth. Okay, next. Ungrounded neutral system with a ground fault on phase B. Here it is phase B. Here is the ground fault at this point. Let there be an earth fault on phase B as shown in figure 3. The faulty phase B will be at earth potential and thus the capacitive current will not flow in this phase. Further, the transformer neutral potential will not remain at zero or earth potential, but the neutral point is shifted from earth potential to the position shown is figure 4. Here is the neutral is shifted from here to here. The two voltages, the voltages of the two healthy phases VR and VY also increases from their value of phase to neutral voltage to full line voltage root 3 times of phase voltage. The voltage to earth no longer 120 degrees out of phase but 60 degrees shown in figure 4. This is the 60 degrees. This is the voltage is equivalent to line voltage root 3 VR and this is VY root 3 VY. This is all going to line voltage. At the same time, the capacitive currents of two healthy phase also increase to root 3 times of their normal value. This is the capacitive current IY2 and IR2. They are increased to root 3 times of their normal value. Okay, next. Here I again represent the figure 4 here to discuss uh, the total phenomena. Here Vye is the voltage to earth of Y phase is equal to root 3 Vy. Vre is the voltage to earth of R phase root 3 Vr. Capacitance current Iy2 under earth fault in phase Y Iy2 is equal to Vye divided by Xye. Xye means the capacitive reactance of the phase Y, and Iy2 again we can write root 3 Vy divided by Xy is equal to root 3 Iy1. Iy1 means the previous original current, capacitive current. Similarly, capacitance current IR2 under earth fault in phase R is equal to IR2 is equal to root 3 VR divided by XR is equal to root 3 IR1. The currents Iy2 and IR2 lead the voltages Vye and Vre by about 90 degree. Here is Vye, this is Iy2, lead it by 90 degree. Again Vre and Ir2 lead it by 90 degree. The fault phase B supplies current IC which is equal and opposite to resultant Iy2 and Ir2. Cy means capacitance of Y phase is equal to capacitance of Cr, capacitance of R phase, or Xy is equal to Xr. The magnitude of IC is given by vector really adding minus I2 and minus IR2, opposite of I2 and IR2, opposite of Iy2 and IR2. The magnitude of IC is equal to minus root 3 Iy2 is equal to minus root 3 IR2. Put the value of Iy2 and IR2 we get. Here is Iy2 value and here is IR2 value. We get the magnitude of IC is equal to root 3 into root 3 Iy1 is equal to root 3 into root 3 IR1 is equal to 3 I phase, root 3 into root 3, 3. So, the faulty phase B supplies a current IC which is 3 times the original line to neutral current of healthy phase and flowing from faulted conductor to ground and leads the original phase to neutral voltage by 90 degree. The VBN or VBE is the voltage and lead it by 90 degree. So as a result, arcing will present in the ionized part at the point of fault. If this arc is maintained, it may exist even after arc fault is cleared. This is known as arcing ground. Okay, next. The intermittent arcing result due to continuous charge and discharge occur on the system capacity in cyclic order owing to inductance and capacitance of the system, due to which high frequency oscillations are established in the system. This high frequency oscillation cause generation of voltage of 5 to 6 times normal phase voltage. This high voltage cause failure of insulation at any point of the system. We know that the voltages of healthy phase increases root 3 times during the fault occurred. If this occurs for short time, then the insulation between each phase to earth is sufficient to withstand it. But if it is existence for long time, may cause the weakening of insulation and result to a permanent failure of insulation. During the earth fault of an isolated earthing system, the capacitive current is inadequate to operate the protective system. Due to these reasons explained above, the isolated neutral system nowadays are not accepted. Earth neutral system has many advantages over isolated neutral system. The various types of neutral earthings are solid earthing 1, 2 resistance earthing, 3 reactance earthing, 4 arc suspension coil earthing, 5 earthing transformer, earthing with earthing transformer. Here I am in this part only discussed about solid earthing and resistance earthing. And the next part, part 3, I shall discuss about reactance earthing, arc suspension coil earthing and earthing with earthing transformer. Okay, next. Here is solid earthing. In solidly earthed neutral system, the transformer neutral is earthed by direct metallic connection. Assumed that the capacitance between conductor to earth in all phases are same and the voltages are balanced. Ground capacitance currents are equal and 120 degree apart. The neutral point of the capacitance being at earth potential. So, no current will flow between capacitance neutral point and transformer neutral point shown in figure 5 and figure 6. Okay, next. Here it is, the solid earthing is continuing. If an earth fault occurs at B phase shown in figure 7, then the voltage VVN will be 0 and the resultant capacity current IC is flow from blue phase and divide into two parts, minus I1, minus I2 and minus IR2. Then it divide into two parts, minus IY2 and minus IR2, and return to their respective phases through the capacitance CR and CY. Here is the capacitance CR and CY. In addition, a second current IF provided by power source flows from fault point and goes to neutral point of the power source through earth path. We know IF is equal to 3EBN divided by Z1 plus Z2 plus Z0. Z1 is positive sequence impedance, Z2 negative sequence impedance, Z0 zero sequence impedance. Zero sequence current is the unbalanced earth fault flows through the neutral. The impedance offered by the system to the flow of zero sequence current is known as zero sequence impedance. This is the zero sequence impedance Z0. As Z0 is mostly inductive, IF lags behind VVN by 90 degree. And thus direct oppose the resultant capacity current IC and reduce the arcing ground. Here it is opposes the IC as neutral point is remained at earth potential under all operating conditions. The phase voltage will not exceed their normal value under earth fault condition. Operation of earth fault relay under earth fault condition is simplified. Lighting arresters can be used rated 80% line to line voltage. The insulation cost of phase to earth is reduced. Okay, next. When it is necessary to limit the ground fault current to a certain value, a metallic resistance inserted between transformer's neutral and earth. However, it is slightly inductive. In figure 9, it is shown an earth fault takes place on phase B of resistance grounded neutral system. The voltage VVN will be 0. The resultant capacity current IC flows from fault point and divided into two parts, minus IR2 and minus IY2, and return to their respective phases through the capacitance CR and CY. In addition, a second current IF provided by power source flows from fault points and goes to the neutral point of the power source through earth path. Here it is the IF, this is the earth path, and goes to the neutral point. The magnitude and the phase relationship of the fault current is depends on the zero sequence reactance value of the power source and the earth resistance's ohmics value. The fault current IF is divided into two components shown in figure 10. IF1 is the one component is in phase with faulty phase voltage and the other IF2 lagging it by 90 degree, IF2 lagging it by 90 degree, and thus direct oppose the resultant capacity current IC at the fault location. Okay, next. Resistance earthing is continued. By suitable adjustment of ohmic value of the earthing resistance, the lagging component of the fault current IF2 can be made equal or more than resultant capacity current IC to prevent the arcing ground. If the arcing resistance is adjusted to a high value so that the lagging components of fault current IF2 is less than the resultant capacity current IC, then the system condition approaches to a isolated neutral system which can result to arcing ground and transient overvoltage. The value of the resistance is so chosen that at the time of an earth fault on any phase, a current equal to full load current of the largest generator or transformer flows in the earth connection. Here R is equal to V phase by I. V phase to neutral voltage in volts. R is equal to resistance in ohms. I is equal to full load current in amperes of the largest generator or transformer. The value of the resistance is so chosen that at the time of an earth fault on any phase, A current equal to the full load current of the largest generator or transformer flows in the earth connection. Okay, thank you for watching the video. If you think the video is useful to you, then please subscribe our channel and share it to your friends. Okay, bye, see you next time.